Hi everyone, today I'm going to speak with you about geometry, intermolecular forces, physical properties, and molecular orbital theory. So some of this should be reviewed for you, but of course we're going to put this in more organic chemistry and um, you know, hydrocarbon terms. Okay, so let's go back to first Vesper. Okay, so that's valence shell electron pair repulsion theory if you're a little cloudy on that. So remember that there are always two electrons, whether either part of a bond or part of some kind of lone pair. Okay, so two electrons establish covalent bonds, lone pairs behaving as a surrogate coordinate like hydrogen. So it's going to take up the same amount of space as that of an actual duet that would tie on a hydrogen to another nucleus. Okay, so negative ions are larger radii with electron density, and then positive ions are going to be kind of shrunken up from their ground state counterpart with decreasing decreased electron density. So electron repulsion positions branch nuclei farthest apart. In other words, if they're going to bump heads and bump uglies and kind of push further away from one another, it's going to kind of influence them to be in one particular axis at a particular time. Okay? So let's go over some conceptual review here. So which nuclei mentioned in each example have a lone pair of electrons about them? So the first would be hydrogen and sodium hydride. Okay, so NaH. Okay, so this is going to have a lone pair because a hydride is going to be a H minus anion. Okay, and that means that that's full duet occupancy for hydrogen. Remember, that's just a 1s subshell. Okay, so then phosphorus and pH3. So phosphorus is going to be in group 5A. So in other words, you're going to have a lone pair there for phosphorus as well. This is going to be isoelectronic to something like ammonia. Okay. So it's going to be sort of a tripod with trigonopyramidal geometry, and of course this is going to be pushed by, sorry, let me fix that up a little bit, fixed by the position of the lone pairs, right? So it's going to be a little bit different. It's going to be somewhat similar to tetrahedral, but again, that lone pair is going to be different than an actual coordinate. Okay, so it's going to be influencing the geometry slightly differently. So let's think of chlorine and ClO4 minus. Okay, so that's going to be this ion. Okay, so you're going to have this negative charge, and it's basically going to make the rounds around this entire complex here and be a stabilized ion as a result. So as, in other words, this chloro group really doesn't have any lone pairs, because remember that chlorine has valence in 7 in the ground state. So in other words, it's an expanded octet with this whole complex with these extra oxygens there. So in other words, no, there is no lone pair. There's a lone pair for pH3. There's also a lone for the phosphorus of pH3. There's also one for hydrogen of sodium hydride. Okay, last is going to be the middle nitrogen and N3 minus. So okay, so we have two double bonds between each nitrogen here. So in other words, we're going to have a full octet about each nitrogen, but we're not going to have a lone pair that's going to be existing here. So in other words, one of these is going to overstep the charge limit, so this is going to be negative and positive to cancel out to be net neutral, and there's going to be a negative anion on the other side. Okay, so let's review and match the following molecules to their proper geometry. So something, again, isoelectronic to pH3 is going to be NH3, an ammonia molecule. Okay, so it's going to be trigonal pyramidal. Okay, and then for CH4, that's going to be tetrahedral, so it'll be similar. CH4 here. Okay, so CH4, 4 coordinates, it's all going to be tetrahedral. Okay, and then acetylene. So acetylene is going to be like so. So we're going to fill out, so this is going to be C2H2. We're going to fill out the octet about each carbon. We have to put a triple bond there between the two carbons. And this two duets on the other side of each other for the hydrogen or CH bonds. So this is going to be sp hybridized. Okay, so this is going to be a linear construct. Okay, so we'll just put that as linear with a straight L. Okay, and then formaldehyde. So formaldehyde, let's go over to the other side of the table here. Board rather. Okay, so formaldehyde is going to be sp2 hybridized, and it's going to be trigonal planar. Because that pi bond that's right there is actually going to fix those two hydrogens in a particular plane parallel to that oxygen. But there's going to be a 120 degree angle. Sorry, yeah, 120 degrees, not 180. There we go. That's better. Okay, so it's going to be 120 degrees side to side to side, and you're going to have a 360 degree full circle. So trigonal planar, again, pi bond fixing everything into one plane. All right. Okay, so let's think about ionized carbon and what kind of geometry we can deduce from, let's say, carbocation. Okay, so this is a carbon that is going to be not so electronegative, but more electronegative than hydrogen. And hydrogen doesn't have a lot of ability to feed electrons in to stabilize that particular charge. So this is going to be an unstable anion. Let's take something that's a little bit more stable, like a tertiary carbocation. So remember that carbon's going to be slightly electronegative, so it's going to want to feed some electron density in there to that positively charged carbon and, stabilize that charge. Okay, so this is actually going to be fixed in a trigonal planar form as previously shown with formaldehyde. But there's going to be a deficiency of electrons in carbon's sort of outer orbit, if you will. So things are going to be exactly 120 degrees apart again per the Vesper and electron repulsion. Okay, so carbanions on the opposite end of the spectrum are going to have that lone pair, and it's going to be negatively charged. And something like this is actually going to be quite stable because this negative charge is basically carbon saying, I'm already good with my electrons, I have a full octet, and I don't need any more input, unlike what is needed right here on the left for a stable carbocation. So this is going to be a stable carbanion. It's going to be a different geometry as well. It's going to be trigonal pyramidal as opposed to trigonal planar, what we see here. So this is trigonal pyramidal. So the pyramidal coming from this sort of tripod figure here at the bottom. So it's going to be shaping essentially a pyramid with that carbon. This is going to be planar, again, trigonal. All right. So let's think about 3 dimensions here. I've already kind of introduced you to this slightly with wedges sticking out of the plane of the board, and then this sort of dash notation that's going into the plane of the board. Now, I've shown you this particular product from a bromination reaction of cyclohexene, and I'm not expecting you to understand what the chemistry is involved with that, but I do want you to understand that bromine is going to be a much larger atom that's projected when you're looking at these particular line structures, right? Bromine is just written there as normal font would be, right? As if we didn't have to shortcut our line structures here, be approximately the same in actual font or whatever, but in actuality, when you're thinking about the electrons and how much, radii this stuff actually takes up, it's going to be pretty considerable. I mean, in terms of bulk and size. So in other words, these have to be kind of fixed on opposite ends of this ring here, this cyclohexane ring. Okay, so with that said, that means they're going to have to be anti to one another with respect to where they are about the plane of the ring. Okay, so it's going to be sp3 hybridized here, so that means they're going to take up 4 different coordinates, or 3 coordinates, but 4 different nuclei to branch off of that particular carbon there. All right, so let's now think about model kits and actually putting these together. So if you want to try for your own exercise, if you've already bought a model kit, you can check that out and build it and see what kind of geometry you're going to get and see where those bromines end up with respect to how your ring is formed and looking. So just some structural considerations here with respect to polarity. So bromine here is going to be most electronegative about this whole compound, right? So if it's sticking out of the plane of the page and going into the plane of the page here on the bottom, it means that overall the dipole is going to go in this particular direction. Now, the bromine is slightly more electronegative than everything else that's here in the ring, so what it's going to do is pull electron density in that right direction. It's going to be right along the plane of the page or board rather, because those bromo groups are actually facing sort of opposite in magnitude with respect to where it's going in that one particular path, so it's additive. Okay, so these are vector quantities. If you were to draw out sort of a dipole sticking out, dipole going into the plane of the page, it's all going to sum up and meet right there where this line arrow is. Okay, and then the way I always keep it is that this is going to be partially positive and it's going to go in a negative direction, or more electrons are going to flow. Okay, so let's think of 2 different compounds here. We're going to think of methyl chloride . Okay, so we have chlorine right there, which is going to pull all that electron density in its direction. Okay, and then we're going to have chloroform. That's going to be a different story because we have 3 chlorines that are going to pull all of the electron density away from this carbon and this hydrogen that's here. Okay? So in other words, if it's facing one direction, it's probably going to face out towards your nose or somewhere in proximity to it. So let's think about some higher order bonds too. So if we have, let's say, something like this, so this is going to be a benzene ring with a cyclohexane ring fused to it. We have some double bonds that are constantly going to be in motion over here. They're constantly going to resonate. So in other words, that's some kind of electron dense, heavy, pi electron environment. So in other words, it's going to pull electrons away from where this ring is, right, and feed it into where there's slightly more electronegativity. Okay, so when you add more electrons to bonds, to make double bond, triple bond, etc., higher order bonds, you're going to see a higher polarity, okay, or more electronegativity. So what does this actually mean for intermolecular forces, which is our next topic? Okay, so let's now talk about solubilizing particular compounds, whether we're just talking about solids that need to go into the liquid phase as one particle or break apart into ionic form. So let's think first about like dissolving like, right? So if we have something that's very much a hydrocarbon, it's not going to go into, let's say, water that has a dipole moment, right? It's going to more likely go into something that's also a hydrocarbon, let's say like heptane or something like benzene. Okay? So, but those are going to be really kind of more weaker intermolecular forces, as we'll see a little bit later. But let's first think of ions in water, right? So let's say we take NaCl, run that through water, and then we're going to get some ionization, right? It's going to be a strong electrolyte. So we're going to form Na plus and Cl minus. We're going to go into the aqueous phase from being a rock solid salt. So going in there into the water phase, things have separated apart. So in other words, these are now particles, right? They're not necessarily part of a particular complex. Excuse me. However, if we have water and it has some dipole moment, right? So where there's partial negative charge over here where the oxygen is. Don't forget your lone pair to kind of show that, and then partial positive over here where this hydrogen is. So electrons are kind of going to go up in that one particular direction. Now these are going to be partial negative and partial positive charges respectively. So there's going to be some kind of particle that's going to match up in terms of charge. So for here, we're going to see Cl minus gravitate towards this partial positive charge that you see over at the hydrogen. Conversely, with sodium plus, that's going to gravitate over to where this partial negative charge is here over oxygen. The most electronegative element is about water. Okay, so this is what is referred to as ion dipole interactions. All right. But think about simple sugars and alcohols. So these are what are referred to as non-electrolytes going into water. They are soluble. Why? Because they have the ability to hydrogen bond. Oops. Let me clean that up. Yeesh. Okay. So I'll just keep it simple with some alcohol here. Let's say I have isopropanol, which can act as either a hydrogen bonding donor or a hydrogen bonding acceptor with water. Okay. So one of these lone pairs is going to coordinate with this hydrogen and kind of share a bond there, right? And this can also act as a donor itself, right? So in other words, it's going to stabilize, the water is going to stabilize and dissolve something like isopropanol that's pretty much infinitely um, dissolving in water. Now, if you, let's say, lengthen the chain of this hydrocarbon here, you're no longer going to be as soluble in water. Why? Well, water kind of likes to fix itself in this sort of matrix, right? Because you have to have these lone pairs that are kind of keeping everything spaced out, and they're interacting with one another at the same time with hydrogen bonding as well. So the more you kind of grow that sort of hydrophobic chain that's there, the less solubility you're going to have in that particular alcohol. Okay, so so hydrogen bonding is really sort of the name of the game, and things that go into water that are not ionized. So in this case, this is going to be the alcohol. So for more hydrocarbon substituents, less soluble in water, so i.e. it becomes more hydrophobic. Okay, so let's think about solubility of diethyl ether and formaldehyde in water. Okay, so diethyl ether is going to be this molecule right here versus formaldehyde. Okay, so both of these have a dipole moment, albeit formaldehyde, since it has that CO double bond, it's going to be much more electronegative. So you're going to have much greater sort of net dipole. Right? So it's going to be much greater going off in one net direction. So that actual data is going to be 2.33 dBi, as opposed to this, which is 1.15 dBi. Okay, so this is going to be about 40 times more soluble in water than acetone is. So that, or sorry, not acetone, diethyl ether. So what that means is that there's going to be some dipole interaction there. So you have to kind of think of it like Legos would come together, right? There's a little bit of extra of that peg that's in there, and there's a little bit of a deficiency underneath the next Lego where that sort of void is, where it's supposed to snap together. Okay, so you can think of like that with dipole interactions. Clean that up. Okay, this is not going to hydrogen bond, right? So we're talking about dipole here. But that partial negative and partial positive are going to line up happily. Okay, so these are little deltas. Oops, that's going to be positive. Dang, messing up here tonight. Okay, so that negative and that positive are going to meet up. And again, that negative and another positive somewhere up the chain are going to meet up. Right? That's way too big. But you get the drift here. So dipole, ion dipole, hydrogen bonding. This is going to be very strong interactions. This is going to be very strong interactions. This is going to be a little bit less so. Now the consolation prize of that is in terms of intermolecular forces is going to be LDF. So London dispersion is just basically going to be instantaneous dipole shifting of electrons just in population in one hemisphere to the next. If you want to think about it in terms of, where the nuclei are to where the electrons take up space. Okay, so anything that we think of in terms of physical properties, right? So some kind of intrinsic properties that all these different molecules have, those all revolve around the intermolecular forces, some of which I've just discussed with you. So we've had dipole-dipole, there's ionic-ionic, and then there's hydrogen bonding, and then there's the lowest on the totem pole again, which is the LDF. So increased molecular weight, more ordered structures are going to be a little bit harder to kind of break apart, right? There's almost like an act of solidarity. Okay, so hydrogen bonding is when two species are involved, and acceptor as well as a donor. So something that has a lone pair is going to be an acceptor. So it doesn't necessarily have to be this. It could be a carbonyl, it could be an amine, it could be an amide, it could be many different things. So something to take into consideration. So I have another example that's right here in your text, or sorry, not in your text, but in your notes in terms of intermolecular interactions. In this case, hydrogen bonding. Okay, so I kind of showed you where charged particles, basically they split off in terms of their charge, going up to a partial positive or partial negative, and that being the ion dipole. Okay, so that's going to be very important when we start thinking about what kind of solvents we're going to use to keep certain things into solution and have a successful reaction. Whether we're under basic conditions or whether we're under acidic conditions, or if we have a swap in ions, etc. Okay, so some of that still does occur in this particular class, but just not as you would see before with metathesis reactions. Okay, so a polar protic solvent is going to be a solvent possessing a dissociative H+. So if you can think of these two, these are both polar protic solvents. Okay? So it's generally with a lower pKa, somewhere around 17 at the highest, right? So polar protic solvents facilitate charge separation upon their solutes. So in other words, something like this, which again is a polar protic solvent, can dissolve and split up those ions fairly well. Okay. Now a polar aprotic solvent is going to stretch a dipole a little bit more than it. So something like this is going to be a polar aprotic solvent, where those hydrogens are not directly attached to any electronegative atom, they're merely attached to carbon. Okay, so in other words, to be deprotonated is going to require a very strong base, and it's going to be highly unlikely with the oxygen looking to pull electron density away. Okay, so with that said, polar aprotic solvents tend to stretch a dipole, sort of like what you see right here, pull those bonds further out so they can interact with other reactive species. Okay, so let's think of a conceptual exercise here, and I'm going to ask you which one's going to be a protic and which one's going to be an aprotic solvents. So let's take the first one, which is ethyl acetate. Okay, so the general dipole moment is going to go up in that direction. There's no hydrogens that are directly attached to either oxygen here. So in other words, this is going to be a polar aprotic solvent. So this exercise is asking you to box polar aprotic solvents. So the next is going to be formaldehyde. That is also going to get boxed, right? Because those hydrogens are not attached to an electronegative atom directly. Okay. So is also going to get boxed. We have something like butanol that is still protic. Okay, so even though, excuse me, you have a longer hydrocarbon tail there, that hydrogen is going to be protic. Just like water, and we've already established that that is going to be a protic solvent. Okay, so that is, sorry, that's going to be, dang, and it's a little late. Fix this bond up too. It's going to be circled, protic. Okay, so then we have another type of ether, which is going to be aprotic because there's no hydrogen attached to any electronegative species. And then DMSO. Again, all the hydrogens are going to be attached to these terminal end carbons or methyl groups. Okay, so that is going to be squared in as well. So these are all polar aprotic. These are all polar protic, or those two are polar protic. Okay, so let's think of some nonpolar molecules. So, but first we're going to go over detergents or soaps. So these are going to be ionic compounds that are going to just have, I'm not going to draw the entire chain here. It's kind of defeats the purpose. You can just say that it's hydrophobic, that's for sure. Okay, what it does is it basically just sponges up other fats and stuff that's gunked up on your dishes or what have you. Right, if you have burned anything onto the pan or what have you, some kind of IMF, some LDF, London dispersion forces, intermolecular forces, to kind of sponge up some greasy molecules that need to go in the gunk, and it's going to interact with the water. Okay, so we have, just call it an R group. R is going to be 17 carbons down, and so this is going to be negatively charged. And then you're going to have this positive charge with sodium. So it's going to be sodium stearate. So stearate is to denote that there's going to be a total of 18 carbons from this position onward. It's going to be a very long hydrophobic tail. It's just like the fats that are in your, cells and what have you, that would basically sponge up everything that's hydrophobic over here. And then these ions would interact and go with some of the water molecules and get rinsed away. Okay, so it basically envelops some fats and other gunk that need to go that would otherwise be insoluble in water. Okay, so that's what is referred to as a detergent. Okay. So there's some different types of conjugate acids of this. So conjugate acid means there's just a protonated form of what I was just talking about here. So this is going to be a carboxylate, but this is going to be a carboxylic acid if you remember back to your functional groups. Okay, so something like soap is going to be really useful in breaking up different types of, let's say, bacteria, right? They could take in some kind of host DNA and do something really bad. So, in other words, something like soap would be good to wash your hands and get rid of any type of living nasty things that are, that you might have exposed yourself to. So it takes out both saturated and non-saturated types of fats. Okay, so remember, non-monoditriester fats are all fatty acid chains, and then they have sort of a glycerin backbone. So there may be 3 esters, 2 esters, and 1 ester. So just like acetate, ethyl acetate that I was showing you earlier, same kind of ester bond. Okay, same business ends, but just different lengths. Okay, so cell walls from let's say sterols, they also affect fluidity, right? So just like cholesterol in your blood cells, right? It's going to affect how well or how smooth or thin everything kind of moves about in your bloodstream, right? So let's talk about some plant and animal hormones. So these are all going to originate from some isoprene monomers. So isoprene is going to look like this, right? And basically you're going to build up things like cholesterol or some kind of sterols, as stated before, beta carotene, things that are psychoactive that you can extract, what have you. Okay, so now we're going to start looking at more of what particular structural properties we're going to see with molecular orbital theory. Okay, so we're going to essentially be looking more at pi bonds than this approach when we start thinking about unsaturation and stabilized double bonds and more unstable forms as well. We're going to think about what kind of orbital overlap we will see with those pi bonds that I just mentioned. Okay, so I wanted to just make a quick correction here. Isoprene is going to be this particular molecule. It's a conjugated diene. It's been a long day. All right, so these pi bonds, as you see here, is not just 1 but 2. They're going to be conjugated to one another. So in other words, for this particular compound, you're going to have some overlap in these pi bonds. Remember that pi bonds kind of fix things in a flat, sort of planar way. So this is going to be planar, this is going to be planar. Doesn't exactly mean that you can't have some kind of rotation about this bond here, but it's going to be lowest in energy in this particular form. You also have to think about pi bonds as opposed to sigma bonds here. So sigma bonds are part of this entire construct, right? But then the pi bonds are actually what are going to be fixing them in place in a particular plane. Okay, so bonds involve electronic behavior. Pretty much that's really the rule of thumb here. Per Heisenberg, the predictability of an electron's location is uncertain, but the probability of its known location is certain. Okay, so you know where it could be at a particular point. You don't just know exactly where the movement is going to be. Okay, so there are 2 types of orbitals to consider. There's atomic, right? So if you just think of p orbitals, they're going to be kind of in this particular fashion, right? So let's say this is px or py. This is going to be pz, right? And then px. Okay, so they're going to be in sort of a lobe or figure eight form like you see here. Of course, if you were to form some pi bonds, right, they're going to have a little bit more p character to them because they're going to sit above and below a particular axis. Okay, and so you're going to engage in some kind of overlap, right? So remember that there's just going to be two p electrons for carbon. So carbon, if you think about it, is going to go 1s, 2s2, 2p2, right? Because it's going to have an atomic number of 6. And, sorry, I'm fighting my cat for plastic here. He's trying to chew it up and not having it. Okay, so you're going to have some p overlap. In other words, you're going to form some kind of pi bond. Okay, so they're going to be orthogonal in shape above and below that sigma bond that would be pre-established, and do that lower energy, more stable first bond. Okay, so orbitals are shaped in which an electron is going to move fast, right? And have the highest probability of occupying a particular space. So as it gets higher in energy, it may form some different type of geometry in the way in which it orbits about particular nuclei or about its particular nucleus. Okay, so remember that electrons repel one another, but if they're an opposite spin, they're going to be able to be of equal energy but an opposite spin with respect to the magnetic field. Okay, so atomic orbitals. So I've talked about s orbitals, talked about p orbitals that you see right here. So s orbitals are going to be more spherical, right? So they're going to be taking up just a particular shape, or not going to have an angle or anything, right? So it's not going to be shifting going into sort of a figure eight motion. It's just going to be just continuing to orbit, sort of like we orbit around the sun, right? Okay, but p orbitals are going to be directional, right? You're going to have x, y, and z. This is just random wherever it can kind of orbit about in a spherical form. Okay, so where is there going to be some kind of overlap with electrons where you can actually establish a bond? All right, well, we can think of molecular orbitals where the electrons are of equal of energy, a lower energy than they would be as their atomic orbital counterparts. Okay, so let's think of constructive versus destructive interference. So let's think of 2 pi electrons. Okay, so here's our little node, or this is where our little nucleus is, somewhere in between, and then we're going to have our sigma bond that's already pre-established between these two nuclei, but we're going to have some overlap above and below where that sigma bond is going to be established right here. Okay, so this is going to be a sigma bond, and I draw my sigma is very ugly, like a sort of warped up looking 6. Okay, and then I have my pi bonds that are going to be just above it and below it. Okay, excuse me. So notice how I put a plus here and a plus here. This is an agreement of phase. It's not going to be an agreement of charge, because in other words they would repel one another. So this is what is referred to as constructive interference. That means that these electrons have kind of blended in and become what you would consider simpatico, or kind of in the same phase. But when they're opposite in phase, like what I'm going to draw here to the right, is when things get kind of cut off. Okay, so there's going to be some sort of nodal plane to where these electrons are actually not going to overlap and orbit with one another in unison. They're going to be furthest apart from one another. Okay, so again, there's going to be one electron from each particular nucleus, and they're going to either work together or split apart and have destructive interference here or constructive interference here. Constructive, if everything's working in unison, and that's going to be constructive. Okay. So let's think of orbital overlap. So we're going to have a sigma bond for s orbital overlap. So 2s, we're going to have 2 s orbitals that overlap, and then you're going to have a sigma bond that's going to be okay. So if we're thinking about bond energy, this is going to be much higher in energy, and this is going to be anti-bonding, and this is going to be bonding. Okay, so this is lower energy, this is going to be higher energy. If we were to put them up on the comparison in terms of low energy, higher energy, this is going to be lower because things are going to be more stable. Okay, so let's think now about hybridization and sigma versus pi bonds. Again, the sigma bonds are going to be the ones that are going to be hybridized, right? So they're going to either take a little bit of p character, a little bit of s character, right? So when you talk about SP hybridized, that means it's going to be 50% spherical and then 50% p, right? Like what you see right here. So it's 1 to 1. Okay, so sp2. That means it's going to be 2 parts p and 1 part s, so it means 1 to 2. Right? And then if it's sp3, it means it's going to be 3 parts p to 1 part s. Right? So in other words, as you change your hybridization to have more s character, the more stable that particular sigma bond is going to be. Okay. Now, pi bonds are going to be higher energy, right? But they're going to actually stabilize the rigidity of a particular bond and make sure it doesn't kind of wave around, like isoprene might, as I introduced before. Okay, so think about what ethane and what ethene are going to look like, and ethyne, right? So as you start adding more pi electrons, like how I had right here depicted, if you add them, an additional set of pi bonds, it's going to have to go perpendicular to this to make a CC triple bond. Okay. Now, if it's tetrahedral, like what you might see right here with this X, Y, and Z of a plane of where as p orbitals would exist in atomic form, once they form or hybridize to become sp2, sp3, sp, they're going to be able to overlap with that sigma bond, let's say that s electron from, let's say, hydrogen. Okay, and then it's going to establish a stable bond somewhere in between the energy of p and the energy of s. Okay, and then ethene is what you're seeing right here, but then you're also going to see some sigma bonds that are going to come out and bond to a hydrogen, maybe bond to the inside. You can see some diagrams of that are going to be much more elegant than what I'm going to put up on the board here in your text, and I can kind of go over some of those with you later, particularly during review time. But let's just think about counting sigma and pi bonds from a line structure now, because what we're going to be looking at right here is really more theoretical. We're not thinking about actual bonds that we're going to be, stripping off and re-amending. Okay. All right. So let's take something like benzene. Okay, so just the line structure of benzene here. And we have 6 CH bonds, so that's going to be 6 sigma bonds. We have 6 CC single bonds, so that's a total of 12 now sigma bonds. Okay, and then CC, another 6 sigma, excuse me. There's a total of 3 double bonds of carbon there, so it's going to be 3 pi. Right. So if you see a pi bond or you see a double bond, that means at least one of those is going to be pi. The first one has to be sigma. Okay. But when you see a triple bond, you're going to see more than one pi bond, as we'll see later. Okay, so let's take this next compound. It's a little Rudolph looking here with the antlers. And it's going to be an aromatic structure. Okay, so we have these 3 methyl groups sticking off of that one carbon that's branching off on each side. Okay. So with that, we have a total of 9 CH bonds for each one of these branches. Right, so that's going to be 9 plus another 9, that's going to be 18. Not going to have anything branching off of this particular carbon that's branching the 3 methyl groups off. You're going to have 2 CH bonds here, one here and one here. Not going to have anything at this junction, not at this junction, and not at this junction. But that's okay because you have 2, 4, 6 more. Okay, so you have 6 plus 2, that's going to be 8, plus another 18. So 18 plus 8 is going to be, 26 sigma bonds from CH. How about from carbon-carbon? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So 22 sigma bonds from CC. Okay, so for a total of 48 sigma bonds. Okay. And then how many pi bonds? 1, 2, 3, 4, 5. Okay, so 48 sigma bonds and then 5 pi bonds. And third here, we have a cyclopropyl group, this ketone here, and we're going to have terminal alkyne. Okay, so let's count all the sigma bonds here. We have 1, 2, 3, 4, 5, 6 from one of these hydrogens, 7, 8, 9, 10, 11, 12, 13 sigma bonds, and then 1, 2, 3 pi bonds. Okay. So once again, 1 here from the CH bond, 2 here from this CC bond, 3 here from this CC bond, 4 here from this CO bond, 5 here from this CC bond, CH6, CC7, CC8, CC9, CC10, CC11, sorry, CH1, 10, CH11, CH12, CH13. Okay, so it's 13 sigma, 3 pi. All right, that's going to wrap it up for this particular lecture. It was a bit much to kind of cram in, but we did it, and we'll go over some more examples with dipole moments and things like that during office hours. So be sure to tune in then if you can't make it. And everyone have a good one. Take it easy. Bye.